In this video, I'm going to be talking to you about oxidation and reduction. When an atom gains electrons during a reaction, its oxidation number is going to become more negative. This decrease in oxidation state is referred to as reduction. When an atom loses electrons during a reaction, the oxidation number will become more positive, and this is referred to as oxidation. Let's look at the following reaction in which manganese 4 oxide reacts with hydrochloric acid to yield manganese 2 chloride, diatomic chlorine, and water. As you can see from the oxidation states, you can see there is a change from the reactants to the products. For example, take a look at manganese, has an oxidation state of +4. Whereas in its product with manganese 2 chloride, you see it now has an oxidation state of +2. This means that manganese's oxidation state has become less positive. It has decreased, and thus manganese has undergone reduction. Now, oxidation and reduction, they occur together. They occur at the same time. So the number of electrons gained by one species is equal to the number of electrons lost by another species. If you look here, I'm going to talk to you about a couple mnemonics to help you remember the difference between oxidation and reduction. So, as I've said, oxidation is a loss of electrons, whereas reduction is a gain of electrons. Take a look at the schematic in the upper right-hand corner here, and you can see that in this case, iron 3+ has been converted into iron 2+. So its oxidation state has decreased, which means iron has undergone reduction. It has undergone reduction because it has gained one electron. If you look at gold, gold goes from a 3+ oxidation state to a 2+ oxidation state. Again, the oxidation state has decreased. So what that means is this is reduction because gold has gained one electron, thereby becoming gold 2+. Now, let's go ahead and look at those mnemonics. The first one I want to teach you is Leo the lion goes grrr. Well, grrr and Leo are mnemonics to help distinguish between oxidation and reduction. So loss of electrons, that is our Leo, loss of electrons, L-E-O. Whereas gain electrons is reduction. So this could help you remember Leo, loss electrons, oxidation, grr, gaining electrons is reduction. Now, if that doesn't work for you, there's another mnemonic. Oil rig, oil rig. Oxidation is loss of electrons. That's what we're talking about with redox, transference of electrons. And rig, reduction, is gain. So between these two mnemonics, you should be able to recall the difference between oxidation and reduction and what's occurring during each. The number of electrons lost by a species is equal to the number gained by a species. So in other words, as the name implies, we've referred to this as redox reactions, oxidation-reduction reactions. So there's two parts here. There's your oxidation and your reduction. Here's an example. Manganese metal reacts with oxygen gas to synthesize a metal oxide. Okay, that's magnesium metal reacts with oxygen gas to make a metal oxide. And we've actually seen this one in lab in class. So let's look at our chemical equation here. We have solid magnesium combining with oxygen. Don't forget, oxygen occurs in its diatomic form, Brinkelhoff. And in this synthesis reaction, it will yield magnesium oxide. Now let's go ahead and look at balancing this. On the reactant side, we have 1 magnesium. Products, 1 magnesium. We're good there. Oxygen, oh, there's 2. It's diatomic. So you're going to need to place a coefficient of 2 in front of the magnesium oxide, which means you'll then need to come over and place a coefficient of 2 in front of the magnesium. Now we have a balanced chemical reaction. Let's assign oxidation states. Recall from the last video, you were given a set of rules for oxidation numbers. So let's go ahead and apply those rules to this equation. We have our magnesium. Well, it is in its elemental form. So that is an oxidation number of 0. Diatomic oxygen. Again, it is in its elemental form. That is an oxidation number of 0. Now let's look at our compound here. Now remember, we're going to start with what we know. Well, in this case, we know both the cation and the anion. We know oxygen, unless it's part of a peroxide, will carry a -2 oxidation state. We know magnesium, which is a group 2 metal, will carry an oxidation number of +2. So we really know everything we need to go ahead and assign oxidation numbers to this compound. We have a +2 for magnesium. We have a -2 for oxygen. Next, let's talk about reducing agents and oxidizing agents. Now, this can confuse students. Let's look at this. A reducing agent is the species that is being oxidized. Well, it's causing another species to gain electrons and thereby be reduced. Again, the species that is being oxidized. So its oxidation number is increasing or becoming more positive. What's it doing? It's giving away electrons. If it's giving away electrons, another species is gaining electrons. Grr, gain electrons reduction. Okay, oil rig, reduction is gain of electrons. So an oxidizing agent, on the other hand, the species that is being reduced, in other words, its oxidation number is decreasing because it's taking or gaining electrons. That's going to cause another species to lose electrons. And that species that is losing electrons is being oxidized. Let's look at our reaction here. In this reaction, magnesium is the reducing agent because magnesium is giving away 2 electrons to form this magnesium oxide compound. We can see the oxidation state becomes more positive or increases, goes from 0 to +2. Along that same logic, oxygen is going from a 0 and becoming more negative. It's decreasing to a -2. Therefore, the oxygen gas is the oxidizing agent in this case, and it is causing another species to be oxidized. And that species being oxidized is the magnesium. So let's look at this example here. Solid iron reacts with oxygen gas to form solid iron 3 oxide. Okay, so we have our solid iron and we're going to combine it with oxygen gas to yield this compound, which happens to be rust. This is iron 3 oxide. Let's go ahead and balance this by placing a coefficient of 4 in front of the iron and a coefficient of 2 in front of the solid iron 3 oxide. And you can see now, because of that, we have 6 oxygen on the right side. So we need to now place a 3 in front of the diatomic oxygen, and we have a balanced chemical reaction. Here you can see a schematic showing the formation of the iron 3 oxide. Let's look at our oxidation rules and assign oxidation numbers to these species. Let's start with iron. It is in its elemental form. Okay, so what does that mean? Its oxidation number is 0. Same with oxygen. Its oxidation number is 0. Now let's look at the iron 3 oxide. Where do we start? Start with what you know. And you know oxygen is going to have a charge or an oxidation number of -2 unless it's part of a peroxide, which it's not in this case. So we know oxygen has a -2 oxidation number. We know there's 3 oxygen. We know 3 times -2 is -6. Now let's look at the cation, iron. Iron must have an oxidation number of +3 because there's only 2 of them. This is not a charged compound. It is a neutral, so we've balanced charge. In the oxygen, we have -6. In the iron, we have 2 multiplied by +3 equals +6. +6, -6, we're all set. Okay, so moving on, I want to reiterate, to put it another way. A substance that is reduced acts as an oxidizing agent, whereas a substance that is oxidized will act as the reducing agent. In this equation, iron is the reducing agent. Iron is becoming oxidized, and so it is causing another species to be reduced. Oxygen is the oxidizing agent. It is being reduced from a 0 to a -2. Because it is being reduced, it is accepting or gaining electrons from another species, and that species is becoming oxidized. Identifying oxidizing and reducing agents. So let's look at some common oxidizing and reducing agents. So atoms, ions, and molecules that have a very large affinity for electrons. In other words, they have a high electronegativity. Now, depending on where we are in the course sequence, you may not be familiar with that term. But electronegativity means the species has a high affinity for electrons. We'll leave it at that for now. Also, species with very large oxidation states, they're more unstable, and they tend to also be really good oxidizing agents. Examples: all of the halogens. We have the chlorine, fluorine, the halogens, and any of those other species in that region of the periodic table that have a high electronegativity, a high electron affinity, such as oxygen and ozone. You can see in this schematic here, a lot of students say, why is lead-4 a strong oxidizing agent? And it has to do with the fact that it's unstable because it has such a relatively high oxidation number of 4+ that it will readily gain 2 electrons to become lead-2+. Well, when it gains those 2 electrons, remember what's happening. Some other species is becoming oxidized. All right, so other common examples of oxidizing agents, some of your strong acids, sulfuric acid and nitric acid, to name a couple. Here are some polyatomic ions that have unusually high oxidation or large oxidation states. If you assign an oxidation number here to chromium in this chromate anion, you'll see its oxidation number is +6. If you look at permanganate and manganese in this ion, it's actually going to have an oxidation number of +7. Those are considered relatively large oxidation states. So these are species that, again, will oftentimes gain electrons and become more stable in the process. Now let's look at some examples of reducing agents. These are atoms, ions, and molecules which have relatively small ionization energies. In other words, they will readily give away or eject their electrons. That's what that term means in case we haven't gone over it in this course yet. A small ionization energy means that these have very low electronegativities and electron affinities. So it's kind of like the opposite of the oxidizing agent, which should, by this point in this unit, make sense. So these are good reducing agents. Let's look at some examples. Group 1 and Group 2 are excellent reducing agents. They will readily give away 1 or 2 electrons to become a +1 or +2 oxidation state to fulfill the octet rule. Well, other species are then gaining those electrons, thereby being reduced. Other examples include zinc, aluminum, iron, and don't forget your metal hydrides like calcium hydride, in which case the hydrogen actually has an oxidation number of -1 and not +1. In this video, we've gone over what oxidizing agents and reducing agents are and what it means for the oxidation and the reduction half reactions. I'll see you guys in class.